Okay, so today we're going to go over section 1C. So 1C, we're talking about sets and Venn diagrams. So I have a few definitions I want to go over first, and then we'll get into Venn diagrams. So in math, a set is just a collection of objects. So it can be people, things, but again, it's just a collection of objects. Then we have a member, and when you're a member, that's the specific object or thing within the set. So a set is the collection, and members are the specific objects within the set. And then we use a Venn diagram, and that's basically a visual. It's a visual way of describing a set. So I'll write here a visual description of a set. So in a Venn diagram, you have circles, and those circles represent sets. And so here I'll draw this out. This is typically what you've seen as far as a Venn diagram go. These circles represent sets, and it's just a visual representation. Now let's look at notation. I'm not going to go over too many, but one notation that's useful is called roster notation. And so with roster notation, we list members. And remember, members are the objects within the set. We list members of sets within a pair of braces. So let's put here. And this is what braces look like. And you list your members within those. That's called roster notation. They're kind of like parentheses. So when you're writing something in roster notation, again, you are listing the members, which is what the set is made up of, and you're just listing them in the pair of braces. That's it. So that's the only thing I want to mention about roster notation. And also, you don't want to list the members twice. And the order is not important. So here, let's write this down. So let's look at the first example here. It says list the set notation to write the members of the sets. So the set of natural numbers greater than 4. So again, if I want to write this in, let's say, roster notation, I would put my brace. And greater than 4 means 5, 6, 7, and this can go on, right? All the way up to positive infinity. But again, I don't want to list all those numbers. So what we do in math is we just put dot, 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 and that implies it's going to go on forever. And you close your brace. So again, roster notation is when we're putting our braces and we're listing the members. 5, 6, 7, those are considered our members within this set. The letters in the word mama. So here again, if I'm writing this in roster notation, I'm putting my brace, and then you're looking at, okay, what letters are there? M, O, again, you're putting commas. I'm not going to repeat this M or this M because I've already included it once. And remember, one of our points was we don't want to list members twice. So M, O, and then the next unique member is A, and that is it. I can close my brace. The dates of July. So July has 31 days. So we would again put our brace, list 1, 2, 3, and it's not necessary to write all the numbers up to 31. You can use these dots again and then say it will end at 31. That's another way to use the dots. If it's at the end of your list, that implies that there is no end point. This is going to go on forever. If it's in between, that just signifies the pattern here is we're going by ones and we're ending at 31, and we just don't intend to write all the numbers out till 31. Okay, so that is set notation or roster notation. And now let's talk about Venn diagrams. So we said Venn diagrams are a visual representation of sets. And so the circles in a Venn diagram represent the sets. Now, there's different types. We're accustomed to, let me go back here. We're accustomed to a Venn diagram that looks like this. I'm sure you've seen that before. And that is a type of Venn diagram, but there are different types. So we want to talk about the relationships of sets. And so the first one is A is a subset of B. And when I say A and B, we use letters to describe sets. So if A is a subset of B, what that means is all members of A are also members of B. And so what that would look like is this. All members of A, so let's have set A. Again, we use a circle to represent the set. All members of A are also members of B. So A is inside a subset of B. B is my bigger set and A is a subset of that. A is disjoint from B. So with disjoint, it means the two sets don't have any members in common. They are essentially separate from each other. So I'll write here, two sets have no members in common. So that would look like this. You have set A and you have set B, and they are separate from each other. Again, that is what disjoint means. And then we have overlapping. A and B are overlapping. And that's when the two sets share just some of the same members. There's just some overlap. So not all, right? Like a subset. It's not completely part of B, but they have some overlap. And that looks like a traditional, here's set A, and then there's some overlap here. And what I mean by overlap is this middle piece. that they have in common. That is an overlapping set. That's probably what you're used to seeing when you think about a Venn diagram. And then we have A is equal to B. So what this means is all members of A are also the same members in B. Essentially, you just have one circle and it's can be referred to as A or B. They're all in the same set. Okay. So we see here again, just more examples here. This would be considered a subset. Right here, you have whales. Whales are a subset of mammals. So that set whales is inside the bigger set mammals. And then we have fish and mammals. And so this depiction says they are disjoint. There's no overlap. They're not touching. They have no members in common, in other words. And then finally, we're looking at doctors and women, and we can say there is some overlap. And that's what this piece right here signifies. There are doctors that are also women. And with that, let's look at example 2. We're being asked to draw Venn diagrams with 2 circles showing the relationship between the following pairs of sets. So let's look at the first one, cage fighters and red-headed people. So this is one set and this is the other. And so when I draw a Venn diagram, I want to think about, well, what are the possibilities? What are the relationships that are possible between these 2 sets? And so that's what was discussed previously. There's 4 types. It can be a subset, disjoint, there's nothing in common, overlap, they share some members in common, or equal to. And so we're talking about cage fighters and red-headed people. I wouldn't say one is a subset of the other. I wouldn't say that they're not related at all, meaning disjoint. They have no members in common. They're not equal. So I would say there is some overlap. And so what that would look like, and I'll do this here, is we have an overlap. And so here I'll say these are cage fighters, and these are redheads. And what this overlap piece represents is that there are some cage fighters that are also redheads, right? There's an overlap. This is overlap. Okay, and then airliners is one set and automobiles. So here, airliners and automobiles are completely different. There is no overlap between the two. You can't have an airliner like a plane and an automobile. They are disjoint. It's not a subset. One is not a subset of the other. They're not equal. So this is a case where we have 2 sets, airliner and automobile, and these are disjoint. Okay, and then the last one here, novels and mysteries. So again, thinking about the relationships between the 2 sets, they're not disjoint like the previous one, right? Because they do share something in common. I wouldn't call it overlap because again, thinking about these 2 sets, I'd like to say the bigger idea here is novels, right? Books. a category of a novel can be mysteries. There's romance novels, there's mystery novels, so forth, right? So this would be considered a subset. So my bigger set would be novels. And inside that are mysteries. Mysteries are a type of novel. This is considered a subset relationship. Okay. Okay, so now we want to direct our attention to categorical propositions. So what a categorical proposition is a claim that a relationship, it's a claim of, of a relationship between two sets. So we usually have two sets. We have a subject, and that would be considered our S, and predicate. That would be considered your P. And we have quantifiers, words that indicate the relationship between the two sets. And that's words like all, no, some are, or some are not. And again, we're going to use Venn diagrams to visualize this. So let's look at the examples here. It says all whales are mammals. So in this instance, whales are your subject. That would be your S. Mammals are your predicate. That would be your P. And when you say all whales are mammals, what you're doing is you're saying, if I were to draw this as a Venn diagram, it would be a subset relationship where mammals is my bigger set, and whales would be a subset of that. That's the relationship there. No fish are mammals. So we have fish is our subject, mammals is our predicate, and no fish are mammals implies that these are two disjoint sets. So for instance, you would have two sets, fish and mammals, and they have nothing in common. They are disjoint. Some doctors are psychiatrists. So in this case, some implies that there is some overlap between some members. So we would draw that like this. And we have doctors and psychiatrists. Some foods are not vegetables. Again, an overlap relationship. You're seeing the word some. So with that, let's look at example 3. And we want to draw a Venn diagram for the proposition. So it says, no carrots are fruit. And then it asks us, is it possible that some carrots are fruit? So if I wanted to signify the relationship there, I'll do this here. We have carrots, that's my subject, and fruit, that would be considered my predicate. But if I wanted to draw this as a Venn diagram, they would be disjoint. Here's carrots, and here's fruit. And with this visual, right, this is a Venn diagram, they're disjoint. With that visual, I can better answer the next question. Is it possible that some carrots are fruit? Well, based on what I just drew here, no, they don't have any members in common. Okay, and then we'll do one more. Let's look at B. Every fish can swim. Every is a key word for me, meaning we will have a subset here. If you take a look at this example here, the form all and every are very similar. And when we did all whales are mammals, that was a subset relationship. Mammals was my bigger set, and whales was a subset of the bigger set mammals. So in the same way, every fish can swim, I would put here swim as my larger set, and fish is a subset. You can put swim or swimmers. And so from this, it asks, can you conclude that some swimmers are not fish? No, all fish are swimmers here. So nothing really new here. We're just translating these propositions, these phrases into a Venn diagram. We're again still looking at the relationship between the sets. So let's go ahead and look at example 4. It says this study was designed to learn whether a pregnant mother's status was a smoker or non-smoker, affects whether she delivers a low or normal birth weight baby. The table below shows 4 numbers, which correspond to the 4 possible combinations of the baby's birth weight status and the mother's smoking status. We want to draw a Venn diagram to represent the table and summarize the results of the study. So looking at this table here, we're comparing a mother's smoking status, so either a smoker or non-smoker, and the baby's birth weight. Now, there will be some overlap here. So the way I draw this Venn diagram, this implies that there's only 2 sets, right? Because the circles represent sets. So what you do here is you pick one status from the smoking, either smoker or non-smoker. It doesn't matter which one you pick. So let's say I pick smoking mothers, right? Mothers that smoked. And then again, from the birth weight stand, you also want to select one, either low birth weight or normal birth weight. So let's say I picked low birth weight, and that would be my other set. You want to pick one of each. Now let's go ahead and see what we can fill in. Before we do that, also, you draw a rectangle outside of your Venn diagram, encompassing your Venn diagram, and we'll talk about what that means in a minute. So now, based on this, let's fill in the information. And I always think it's easiest to start with, you see this piece right here where there's the overlap? That means mothers that smoked and had a low birth weight child, and that would be this value right here, 18. And then we have to figure out, well, what does this piece right here mean? It's strictly just mothers that smoked, right? So when we look at that, we're looking at mothers that smoked, but also you see how this piece, and let's see if I can highlighted some. This piece that I'm talking about is not connected to low birth weight babies. So really what we're interested in is mothers that smoked, but they did not have low birth weight babies. That would be, they had normal birth weight babies, but they still smoked. So this is 132. Next, let's focus on, and I'll try to do this in a different color. Let's focus on this piece. This piece signifies low birth weight babies. And you see how it's not attached to smoking mothers that smoked. So low birth weight, non-smoking mothers, 14. And now if you look at our table, 3 numbers are circled, which means those are the 3 that I've used so far. There's one value that I didn't use, which is 186. And that 186 represents normal birth weight babies from non-smoking mothers. Look at my 2 sets in my Venn diagram. They're smoking and low birth weight. So this is where my rectangle comes in. Something that is not a part of those 2 sets would go on the outside. You see, my 2 sets had to do with smoking and low birth weight, but the 186 represents non-smokers with a normal birth weight. So that would go outside in the rectangle. And that is how you represent this table in a Venn diagram. Okay, let's take a look at example 5. In example 5, we want to use the Venn diagram to answer the following questions. Assume that all the people at the party are either single or married. So it says, how many married people at the party are not under 30? So let's look at this Venn diagram. The 2 sets we have are married and people under 30, right? That 15 represents people that are married and under 30. And you see this 28 outside in the rectangle. That must mean they're not married, so single, in other words, and these people are not under age 30. So single and older than 30, that's what the 28 represents, right? So going back to the question, how many married people at the party are not under 30? Well, we know they have to be married, right? Because the question states that. This 22 here, so I'm looking at the married circle. Only the value 22 represents people that are strictly married and has nothing to do with this pink circle, which represents under age 30. So strictly married and not under 30 would just be 22. How many single people are at the party? So it says single, and it doesn't say anything about age. So if I'm interested in single, I am not going to pay attention to this blue circle or anything encompassed in this blue piece at all. I don't care about that because anything in that is married. So if I'm looking at just single and I don't care about the age, the only 2 values left are 28 and 16. And that is 44. 44 people at the party are just single. How many single people at the party are under 30? So single means I don't want to look at this married bubble at all, right? So I care about single and also under 30. So again, don't pay attention to anything in the blue circle because that signifies married. So I have the 28 and the 16, but they have to be single and also under 30. The only one with single and under 30 would be 16, because the pink circle represents under 30. 28 represents single but over 30. And then last, how many people at the party are not under 30? Okay, so not under 30 is what I'm looking at. So I don't want to focus on this circle because that's under 30 and I want not under 30, which means over 30. Well, and we don't care about relationship status. It doesn't say they have to be married or single. So that leaves us with these two values, 22 plus 28, and that is 50. Okay. So next, let's look at example 6. So it says, draw Venn diagrams for the following groups of 3 sets. Describe the members of each region or state that a region has no members. So we're dealing with hockey players, figure skaters, and men. And so because I don't have a lot of room here, I'm going to use the discussion number 3, and I'm just going to write instead the new sets here. This is the first time we're being introduced to a Venn diagram with 3 sets. Again, the circles represent sets. There are 3 sets here. And so I'll write here, instead of school sports, I'll put men. And then I'll just put hockey. And here I'll put skaters. Okay. And then what I want to do is, there's a lot of different regions now because of this overlap of the 3 sets. And I want to describe what they all mean. So I'll do that in a different color here. Let's first, I think the easiest thing to do is discuss the overlap. And so I want to bring your attention to this piece right here, the middlemost region. This piece is where all 3 sets overlap. And so what that means is we're talking about men that play hockey and also figure skate. So I'd write over here, men. I'll say men that play hockey and figure skate. That's what that means. And then let's look at this middle piece as well. But this middle piece is overlapping men and hockey. And so this is men that play hockey or are hockey players. Let's look at this overlapping piece. And you look at what overlaps here, skaters and hockey. So this would be, now also I want to note here, men is not part of this piece. So that implies these are women that skate and play hockey. And then this final overlapping piece, so we just looked at all the overlaps. It is shared with men and skaters. So this would be men that skate. Next, I'll now do this in a different color. Let's look at this piece right here. This piece would just be men. And so I would say here, this is men that don't play hockey or skate. Strictly just men. This piece, we're just interested in hockey. It doesn't overlap with men or skaters, so that means just women that play hockey. And finally, this piece here, we're just looking at skaters now. They don't overlap with men or hockey, so that means women that figure skate. Figure skate, and maybe I can put here, they don't play hockey. They only figure skate. And the same thing above, when I said women that play hockey, I could also specify here they don't skate. Okay, so that is our introduction to 3 sets that have overlap. The next example I want to do is example 7. It says, use the Venn diagram to answer the following questions. Assume that all people at the conference are either local or not. So the first question is, how many people at the conference are employed, have a college degree, and are local? So when we look at this Venn diagram, the 3 sets are local, college degree, that's represented by the pink circle, and employed. It's represented by the white circle. So the first thing is we want to look at people at the conference. They are employed, have a college degree, and are local. Well, that means they are overlapping all 3 sets, which would be this innermost piece, 11. Next, how many people at the conference are employed and not local? All right, so let's look at this. Employed, but not local. So when we do that, we're focusing on this employed column, or I'm sorry, employed circle, this one. But it does say not local. So you see this local circle. I don't want this piece because it overlaps with local. We want not local. So that means 6 and 16. They have to be in the employed circle, but not local. So 6 plus 16 is 22. How many people at the conference are unemployed? And I just kind of underline so I'm clear on what we're being asked. Unemployed, not local, and don't have a college degree. So 11 was all 3 in common, right? And what we're being asked here is none of these 3 are overlapping now. We don't want to look at anybody in the employed circle, anybody in the local circle, or anybody that has a college degree. So essentially nothing in these 3. And so that would be the only thing left is 3. 3 people were unemployed, they weren't local, and they did not have a college degree. And the last question here, how many people in total are at the conference? Here we would be adding all the values. That would be 77. Okay. And the last example we'll do is example 8. So here we have a technology survey. A survey of 150 college students revealed the following data on the numbers of them who use smartphones, tablets, and or laptops. So we want to draw a 3-circle Venn diagram that summarizes the results of the survey. So from the question, I see that there are 3 sets: smartphones, tablets, and laptops. So let's draw the 3 sets, and I'll do that right here. We have, I'll call this smartphone, and then overlapping with that, we have a laptop, and then overlapping here, we have tablet. Okay. So I always like to start with the innermost middle piece, which is right here. And that means they have a smartphone, laptop, and tablet. So who has all 3 devices? We see here all 3 is 1. Okay, and let's not forget, we'll put a rectangle around this. And what that signifies is someone that doesn't have any of these devices. And we see there's a category for that. None would be 2. So that's where you would put the 2. Okay, and then we can just go reading straight from the table here. It says smartphone only. Well, smartphone only would be right here, 51. Does not share a laptop or tablet, so just smartphone, strictly smartphone. Okay, so we did that. Tablet only. Well, tablet only means right here. They just have a tablet. They don't have anything in common with smartphone or laptop. Laptop only, that would be 12. That goes here. Again, not being shared with the other 2 devices, only laptop. And then in our next column, smartphone and tablet only. So look at the smartphone and tablet circles and look at where they have a common piece would be right here. That's 35. And then smartphone and laptop only. So look at smartphone and laptop, where they share overlap would be right here. And finally, tablet and laptop only, that's shared right here. That would be 4. So now we can answer the following questions. How many students used at least a smartphone? Now, when you think about at least a smartphone, it means they have to have used a smartphone, but any combination of the other devices is fine as well. So really what I'm doing is I'm adding anything in this smartphone circle. That's what at least a smartphone means. So I would be doing 51 plus 37 plus 1 plus 35. And if I do that, I'm getting 124. Next, how many students used a tablet or a laptop? Now, a tablet or a laptop means I'm looking at the tablet circle. So let me erase this highlighted piece. I'm looking at the tablet circle, and I'm also looking at the laptop circle, and I'm adding all those values. Tablet, so I'm looking at this tablet circle and laptop circle, and I'm adding those values. Tablet or laptop, so it can be either or. So that's 35 plus 1 plus 8 plus 4 plus 37 plus 12. And if you add those values, you should get 97. Let's look at the next question. How many students used a smartphone and a laptop, but not a tablet? So let's erase what I just highlighted here. Oops. Sorry, it seems like that got erased. Let's see if I can do it one more time. Okay. So how many students use a smartphone and a laptop, but not a tablet? So here, I just want smartphone and laptop. That would be 37. It's not interfering with my tablet circle. I'm only looking for the overlap between smartphone and laptop. How many students used exactly 2 devices? The people that use exactly 2 devices, look at overlap with exactly 2. I'm going to mark them like that. Exactly 2 devices. So that's 37 plus 35 plus 4. And if I add that, I'm getting 76. Final question, how many students used a laptop or a smartphone, but not a tablet? So here, I look at the smartphone and laptop, and I'm adding values that are in those circles, but not in the tablet circle. So for me, that would be 51 plus 37 plus 12, and that is 100.